question was, how do we make sure that the samples were given to us by surgeons, it's a normal, and then the tumor samples as what they claim is a tumor sample. So we've done our own HNE staining to identify tumor cells, tissues, cuts from tumor cells, and then the normal. You can see there are a huge number of slides to show that, and we only process the samples that they present a normal tissue. In the previous slide, you can see some of the tissues were only obtaining adipose tissue. This is the difficulty of having tumor from breast tissue, that many adipose tissues could be there, and it will not represent the criteria we want for our samples. So two-dimensional electrophoresis were performed in many samples representing many stages of the disease, from stage 1 to stage 4, with some samples of and we compared using a Biorad BD-Quest software. We compared the protein expression among samples presented for us from different stages of the disease. This graph shows number 1, for example. Of course, the software, there are biomarkers where we can use them to make sure that one represents the same sample from the same tissue, from different tissues, and then they are both from stage 3 patient. Many spots were identified. The spots of interest were then excised, and then they sent for magnetop analysis, mass spectrophotometer to identify the proteins we have. We had a huge list of proteins that some of them reported previously, some of them they were reported for the same time. Many of these proteins, I will not go through this list of proteins. Many of them, they were overexpressed. Some of them, they were down-regulated in the tumors in comparison with their adjacent normal tissues. Some of them reported previously, some were reported for the first time in tumor tissues. But we were interested particularly in a protein that is called calreticulin. It's a calcium ion chaperone protein. It was reported previously in many studies in cell lines that it will be overexpressed in tumor. But in our studies, there was an interesting part about calreticulin, is that this protein with many tissues representing many stages of the disease, we can see in the tumor it will always be overexpressed in comparison to normal. But then as we progress with the stages of the disease, these samples are from different patients of representing different stages. We can see that calreticulin expression will be more, and then all of a sudden it will be decreasing. And then when we reach the sample represented by eye, this sample represents a patient with metastasis. We can see that calreticulin level, it will go down. So then our hypothesis at that point is that it could be that there is something in relation to calreticulin in the samples or in patients that will have something to do with metastasis or have something to do with the progression of the disease. So we did Western blotting on the samples from cell lines. We can see that in normal cells there is certain expression of calreticulin. In MCF7, which is non-metastatic, there is overexpression, and MDA, which is a metastatic cell line, the expression of calreticulin is overexpressed, but it's less than those tissues that they are not represented or they don't have metastasis. And the same that we can see stage 3, then stage 4, the metastasis, the expression of calreticulin is going to be down. So what we did is real-time PCR to detect the level of expression of gene expression of calreticulin gene. In stage 1, 2, 3, and then stage 3A, 3B, 3C, and then in stage 4 samples or patients represent stage 4, we can see that calreticulin expression, gene expression will go down. So this was the finding of our study. That was later on continued to figure out what is the role of calreticulin in breast cancer and metastasis, or what's going on? Why did the calreticulin go down? So microarray studies was full. I'm not presenting the photos. Microarray was full, and then there is a rule that in certain pathways that represent calreticulin has an involvement in metastasis of breast cancer, and this work is not yet published. So in conclusion, we can use proteomics approach to identify protein markers or disease markers that could be related to the progression of the disease, or it could be some other protein markers that could have a good source for further studies to be for vaccines like GP96. There is a vaccine, FDA just approved a vaccine in melanoma that targets GP96. In breast cancer, nobody reported them in tissues, but in cell lines it's reported to be overexpressed, but nobody has worked on it on a vaccine for breast cancer. So we might see this in the future. And with this, I conclude my presentation. Thank you.
Thank you, Dr. Alama. Now we have questions, starting due to the lack of time for each presenter, only one question. Please, continuation of the questions during the coffee break. Questions for Dr. Hatem.
Dr. Hatem, I would like to ask you about the diffusion mechanism of the particle. You have talked about the core shell, but you didn't identify the core it's made of. And how is the stability of coating for the core shells when you take care of the temperature, for example? Might be the coating diffused from the second layer in terms of layer. I don't know how you will comment on that.
Well, our studies were not mechanistic, but the core shell system refers to the fact that you would have a drug-containing segment or layer surrounded by another layer that would control the drug release through it. So in the systems that I've described, basically the drug release is a function of water penetration through the semi-permeable membrane of eudragets or polycoat SR, dissolving the drug, and then down the concentration gradient, the diffusion of the drug through either microchannels or by simple permeation and diffusion through the continuous membrane coating. So this is the mechanism. Now, once you go for a monolithic particle, just like many tablets that I mentioned, without the coating, you would have also the formation of gel and then gradual erosion of the gel, forming small particles, reducing the path length and accelerating the drug release, and that's what we saw. So basically, this is the mechanism. Now, there are a lot of variations on it. You can modify the permeability of these coatings by either mixing high permeability and low permeability polymers, or by mixing water-insoluble polymers with water-soluble polymers, or adding surfactant molecules, or adding water-soluble materials. All of these approaches can be used. Now, in terms of the heat stability you mentioned, like in a stability testing, yeah, the results that I've shown for the first work by Haytham Ahmed on the diltiazem pellets, we've done a stability study, an accelerated stability study at 40 degrees C and 75% relative humidity in high-density polyethylene bottles. The pellets were packaged into hard gelatin capsules filled into these bottles and put in the stability chamber, just like you would do for a product that we're developing in a company. And we had a good stability of drug release profile. We're always worried about aging with these systems, but these were stable. Thank you.
Thank you, Dr. Hatem. Any questions to Dr. Karen? Nobody is interested in sleep, everybody. Everything was crystal clear. Thank you. For Dr. Iyad? Sips coffee. Requested. And for Dr. Alama?
Thank you, Dr. Alama. I recommend you, if you are still interested in this kind kind of work and checking out the gene profile and protein profile for the MCF7 and other related cell line, breast cancer cell line, I recommend you to change the in vitro conditioned medium. Again, there is latest work that the high glucose, low glucose, and other parameters might play critical role in upregulating and downregulating of the gene. So it will be quite interesting. Okay, thank you.
Just to comment, actually what led us to start working with human samples is that we don't want these changes from in vitro to immune system. Even though it's very difficult to get samples from humans, you have to go through a lot of ethical committees to get samples, but I'm interested more in human samples. So now this research, we are working with the human samples. We are now collaborating with KHCC. We are getting samples from them, breast cancer samples, and we are continuing our work on human samples rather than cell lines.
Yeah, okay. Thank you for talk. I'm not sure if you are aware of the new techniques for breast cancer detection, mainly for the ductal carcinoma insertion. There's a new techniques without going into this tedious work or the stuff you have done using radiation. Especially from an accelerator. So with a beam, like a beam from infrared beam line, you can detect everything without going into this lab work. So with the kit, with chemical images, you can identify everything with the. Yes.
My aim was not to go for a statistical background, so my aim was mainly to look for drug targets, mainly to see what the pathogenesis of the disease itself, what happens inside the cell. So later on, once we develop the drug towards personalized medicine, then we have this group of patients, they have this profile, genetic or protein profile, they will be benefiting more from this type of therapy. The rest won't. Even my detection is not my area. I'm not interested in how to detect the disease. It's more of how the pathogenesis happens and how I can target treatment for this type of patients rather than starting with chemo, and then estrogen therapy, and then later on I will have a relapse in patients. This work is basically aiming towards personalized medicine in the future for patients. So it's not about detection of the disease.
Thank you at the end of this session. Thank you for all presenters for their very nice lectures, and thank you for the audience. And we have some certificates for those who are presenting today. And please pass by. Okay, good.
الدكتور عمار معي، الدكتور عمار مش موجود، انا بوصله اياها. في هون عندنا دكتور
بروفيسور هاكونارسون. Professor Yolanta is also not around. Dr. Hatem Hatem.
دكتور كارم الزعبي.